Hi, my name is Massimo and I was the second mechanical engineer working on this project.
My name is Bob Bradford. I'm a senior at the University of Arizona, and I'm studying electrical and computer engineering.
My name is Ezra Carnes, and I'm an electrical engineer.
My name is Nick Ortega, and I am a systems engineering major.
My name is Austin Pearson, and I am a computer engineer.
My name is Michael Ziska. I am a mechanical engineering major, and I was also the team lead on this project. To introduce our project, here is a short clip about the Large Binocular Telescope.
The Large Binocular Telescope is one of the world's most technologically advanced telescopes. Sitting atop Mount Graham, a 10,700-foot mountain in southeastern Arizona, the LBT utilizes two giant 8.4-meter primary mirrors that allow astronomers to explore distant planets in our galaxy and obtain crucial knowledge about the origins of our universe. With the utilization of next-generation adaptive optics, the LBT will attain the resolution of a 22.8-meter or approximately 75-foot telescope. This allows the LBT to achieve its potential as the world's most powerful optical telescope.
Right now, the Large Binocular Telescope Observatory is looking to develop a method of testing/debugging the primary mirror cell actuator control boards to verify they are operating correctly. These actuator control boards are custom-built PCBs responsible for the calibration and alignment of the two independent 8.4-meter mirrors located in the primary cell actuator assembly. Currently, the entire actuator assembly is replaced if discrepancies are detected in the system. This solves the problem, but is extremely time-consuming and lacks clarity as to what caused the issues. Our team worked with LBTO to develop an efficient, low-cost microcontroller-based test tool/testing system to verify the functionality of the primary mirror cell actuator control boards. This allows LBTO the option of only replacing a defective actuator board rather than replacing the entire actuator assembly, as well as determining if a faulty board is repairable or not.
Here you can see our system requirements. The vast majority, probably about 75% of them, were going to be electrical based requirements, and the size, weight, case durability probably accounted for about 25% of them. All of them passed. The accuracy we confirmed with a test and analysis that the analog signals were going to be within 5 millivolts of the expected value. The automation was demonstrated, that the systems tests are automated. The power supply was within 3%, being 4.85 volts and 5.15 volts. The size weight requirement was less than 5 pounds, so that passed. The case durability also passed. The data archiving was tested and demonstrated to verify archived results in the database. The user interface demonstrated that the GUI is used for user command and control.
For our design concept, we wanted a handheld tool that would allow for operators to integrate in with the circuit in place in the mirror cell, but also versatile enough to act as our test tool if they wanted to test the control boards in a lab. We decided to get an RS-232 to 422 converter. For the actuator board has a 422 to 232 converter on hand, so rather than writing up our communication lines in RS-422, we decided to simplify it and just use an RS-232 communication, which would relay back our test commands to and from our host computer to the control board and back to decide whether or not a board was faulty or was working properly. Our channels of communication was USB from the laptop to the test tool, and then DB9s to and from the control board. Our main issue was creating a system that was handheld so that an operator of the mirror cell would be able to test the boards in place. We came up with strategic ways to prevent shorting and analyzed our power systems so there would be no overvoltage or overcurrent within our system that would potentially fry the test tool or the control boards themselves. In the control board operator manual, there was a list of test commands, so we mimic them with our test tool, sent them to the board, and analyzed them on a pass-fail basis. If we got the proper response, it was a pass, and if we didn't receive communication back from the control board, simply it would be a fail looking into the system. So we just followed these tables and decided what was a pass and what was a fail from the communication side.
Here's a quick overview of the general test routine for our system. The host computer or laptop sends commands to the M1 actuator board and receives the response from either the actuator board or the test tool Matilda. This is specified in the table of test commands shown previously. Next up is a quick demonstration of how you would go about using the GUI. This is a quick demonstration of how you would go about testing a board using the application. Starting from the test page, after connecting the devices, enter a name you want to give the test, as well as the board number for the board you are testing. Finally, choose whether the board is single axis or dual axis, and then all you have to do is click Run and wait for the test to finish. This is what the test page will look like upon completing a test. The general results of the test, as well as an evaluation for the board, are given at the bottom right. If you want a more detailed view of the results, press the Review Results button. Upon pressing the View Results button, you'll be redirected to the database page, where the commands that failed for your administered test are given on the table to the right. You may also view results for other tests by selecting or clicking rows from the table in the middle. For more information on the application and the test performed, see the user manual. This can be found as a PDF within the project's directory, or by selecting the user manual tab at the top right of the application.
Here is a display of the handheld portion of the project, what we named Matilda. The case consists of two halves, which are 3D printed to include standoffs to support 2 PCB boards, as well as 7 pass-through holes for multiple gauge cables. As you can see in the picture, the corners of the case have been cut to set a moldable rubber compound to give some shock compliance to the case, as when cubes fall, they tend to hit a corner. The cables are secured with undersized O-rings that clamp onto the cable and are constrained from being pushed in or out with slots in the case. The deliverables to the sponsor are 2 handheld Matildas and the accompanying software, which includes the graphical user interface. In addition, a user manual will be provided to aid in training and operation of the device. Lastly, all of the technical data produced during the project, including part drawings, wiring diagrams, CAD files, etc., will allow the observatory, if necessary, to manufacture more.
The lessons that were learned during the project were several and include ordering materials in advance. In fact, backlogs in procurement can severely delay the progress of a project. Also, due to the multidisciplinarity of the project, keeping a flexible approach during the design phase is critical, as it is during the testing and prototyping phases. Committing more time into identifying and researching the correct and most appropriate hardware is very important, as well as it will save time later. Not procrastinating on tasks, that is definitely important as well, and definitely planning a better roadmap would have helped us not committing some of the design mistakes that made us fail early on. This concludes our video. We wanted to give our special thanks to Dan Cox, Slavomir Bucky, James Riddle, Ken Willard, and Gary Redford for helping us during this journey.